Section 16.4, Green's theorem. The positive orientation of a simple closed curve C refers to a single counterclockwise traversal of C. Thus, if C is given by the vector function r of t, where t is between a and b, then the region D is always on the left as the point r traverses C. So imagine that we have some person standing along the curve and they just walk along. Notice that if you look at the person's left hand, it points towards the curve, inward. So that's what we mean by positive orientation. So we need this definition because Green's theorem says that if C is a positively oriented, piecewise smooth, simple closed curve in the plane, so one of these guys, and D is the region bounded by C, then if P and Q have continuous partial derivatives on an open region that contains D, then the line integral of P dx plus Q dy will be equal to the double integral of the partial derivatives, partial Q with respect to x minus the partial of P with respect to y. So you have to be a little bit careful over here. Notice we have P dx in our line integral, but when we take the partial, we take that with respect to y. And similarly, we have Q dy in our line integral. When we take the partial, we take it with respect to x. So Green's theorem is kind of cool because it links up line integrals and double integrals. However, it's very difficult to prove, at least in full generality. You could prove it for simple regions, which are regions that are simultaneously type 1 and type 2. What you do is you draw the region first as type 1, so maybe something like this. And then after you draw it as a type 1 region, you compute the double integral. And after you compute the double integral, you compute the line integral. So what you have to do is you have to break it up into each of the piecewise smooth curves that make up the region. So you can call this one C1, you can call this one C2, C3, and C4. You compute each of the line integrals over C1, C2, C3, and C4, and you show that altogether the line integral over the entire curve C is in fact equal to the double integral. But you do that by doing it in parts. So for the type 1 part, you do the line integral of P dx. You show that is equal to the double integral of minus partial P with respect to y. Then what you do is you rewrite the region as type 2 region, taking advantage of the fact that we're assuming it's simple. And you do the opposite. You compute the line integral of Q dy over the entire type, will be type 2 in that case, and you take the double integral and you show that those are equal. But even then, after doing all of that work, all you get is the proof of Green's theorem if it's a type 1 and type 2 region simultaneously, a simple region. Whereas notice that is not what we're assuming over here. We're assuming that it's much more general. It's just some smooth, simple closed curve. So to prove that in full generality is beyond the scope of the course. So we're just going to take advantage of the theorem without proving it. Just so you know, the notation with a circle around that line integral indicates that we're doing the line integral in a we're calculating it using the positive orientation of the closed curve. You might also see it with an arrow to indicate the orientation. We're not going to use the arrow much though, but we will use the circle. We basically will have that come up whenever we don't specifically say that the orientation goes from one place to another, in which case we'll just throw in the circle to indicate the orientation so we don't have to talk about it anymore. Last but not least, we have another piece of notation for the boundary curve. Instead of writing C, we can write this partial derivative sign next to D, which we use to indicate the boundary of D. So then instead of the line integral over C, we have line integral over boundary of D, and that kind of shows you a little bit more about how D and C are related. So how about we evaluate this line integral, where C is the triangular curve consisting of these line segments. So let's try drawing our curve C. So it'll be something like this. And we're going to go from 0, 0 to 1, 0. So here's two of our points. We're going to go along like that, and we're going to then go from 1, 0 to 0, 1. So along over here to 0, 1. And then from 0, 1 back to 0, 0. So this is our curve C. So that means that this will be our boundary D. Well, it'll be the region D bounded by C. And we need to have some sort of equation over here, it looks like, if we want to do a double integral. So we need to know what this is over here, if we're going to end up writing this as a type 1 region. So in which case we would indicate from bottom to top. So the bottom's easy. That's just when y is 0. So this top over here is also actually pretty easy. Notice the y-intercept is 1, and the slope is -1, so we could say this is y equals 1 minus x. So now we have, from our line integral that we're given, p is the next to dx, q is next to dy, so p is x to the 4th, and q is xy. So then our line integral over c of x to the 4th dx plus xy dy can be rewritten using Green's theorem as the double integral over d of the partial of q with respect to x minus the partial of p with respect to y. So we always have x before y, but we swap p and q in the order when we do our double integral. So now we use Fubini. We write this as an iterated integral from 0 to 1, and then from 0 to 1 minus x, and our partial of q with respect to x is just y, and the partial of p with respect to y is even better, it's just 0. So we have dy dx, because we're doing type 1. So we get the integral from 0 to 1 of 1/2 y squared from y equals 0 to y equals 1 minus x. And that becomes half the integral from 0 to 1 of 1 minus x squared, which is -1/6, 1 minus x cubed. Quick mental substitution from 0 to 1, which is 1/6. So notice that in this case, computing the double integral is way easier than computing the line integral directly. You'd have to compute 3 line integrals over here, whereas we only have to compute 1 double integral. Okay, how about this line integral, 3y minus e to the sine x dx and 7x plus square root of y to the 4th plus 1. C is the circle, so we'll try doing a double integral over the circle. Notice that they didn't give us the orientation, but they kind of did because they gave us this little circle symbol, so we know that the orientation of the curve is positive. So that means that if we want to compute this line integral over the positive orientation, we have, just rewrite it, 3y minus e to the sine x dx plus 7x plus the square root of y to the 4th plus 1 dy, and we're going to make this a double integral. So how about the double integral over d, where d is the disk, so it's inside the circle, and that'll be the partial with respect to x of q, so that's 7x plus the square root of y to the 4th plus 1, and then minus the partial with respect to y of p, which is 3y minus e to the sine x. And we will, how about use polar coordinates, because we're integrating over a circle. It seems to work probably better, so theta will go from 0 to 2 pi because we have the entire circle, and the radius of the circle is 3. So we'll go from 0 to 3 for r. And then, let's see, we've got this partial with respect to x is just 7 because this constant, it disappears, so that's nice. And then this partial over here with respect to y is just 3 because this is constant, it disappears. And in polar coordinates, dA becomes r dr d theta. So we end up with, we can split this because all our theta functions and r functions are separate. So we have 4 times the integral from 0 to 2 pi of d theta times the integral from 0 to 3 of r dr, which is just 36 pi. This is not the only way you could have done this, though. If you wanted to, you could have avoided polar coordinates. You could have just said that the double integral over d of 4dA is 4 times the double integral of 1dA, which is the area of the disk. So that's 4 times the area of a circle, which is pi r squared. So that would be pi times 3 squared, which is 36 pi. Next up, what if we want another formula for the area of a region? Remember that we said the area of a region is the double integral of 1dA. So that means that we want to choose functions of x and y, p and q, so that when we take their partials and subtract, we get 1, because that's what we double integrate when we use Green's theorem. So in that case, we could take p equals 0 and q equals x. Then you take the partial of q with respect to x, you get 1 minus 0, which is 1, so this works. And then if you take p equals minus y, you take that partial with respect to y, you get minus 1, so you do minus 1, and you get 1, so that works when q is 0. And the other possibility is that p is minus a half y, and then q is half x. Taking the partials gives you half minus a half, so it's half plus a half, which is 1. So in the first case, if p is 0 and q is x, then you just have the integral of x dy. In the second case, when p is minus y and q is 0, you just have the line integral of minus y dx. And then when p is minus half y and q is minus half x, then you could just take out the half and you get half of the line integral of x dy minus y dx. So since all of these result in this thing being 1, they all result in a double integral of 1 dA. So we convert back using Green's theorem, and we see that all of these represent the area. So how about we use one of them to find the area enclosed by the ellipse x squared over a squared plus y squared over b squared equals 1. So the area of a general ellipse. So what we'll do is we will parametrize it so we can do a line integral. So we'll say that x is a cosine t, y is b sine t, and t goes from 0 to 2 pi. So then our area, how about we use this last formula, because everything will cancel nicely. So we'll say that that's half of the line integral over c of x dy minus y dx. So what we're doing is half of the integral from 0 to 2 pi. Let's see, x is a cosine t, so we'll have a cosine t. Then dy, let's see, that would be b cosine t dt when we take the derivative. And then we need to subtract y, which is b sine t, times dx. We take the derivative, we get minus a sine t dt. Okay, so that's wonderful because now we have ab cosine squared minus minus is plus, plus ab sine squared. So we factor out ab, and cosine squared plus sine squared is 1. So we're just integrating 1 dt from 0 to 2 pi. So that's just 2 pi, 2's cancel, we get pi ab, which is the same as what we've calculated before. Okay, how about we now evaluate this line integral? the curve C is slightly more complex, but even though we didn't prove Green's theorem for these more complex regions or even talk about it, like we said, it can be proven. So we're just going to take advantage of it. We'll draw these semicircles. So let's see, we have a semi-annular region. So an annulus is when you've got like a circle with a hole in the middle. So in this case, we have semicircles with a hole in the middle. So x squared plus y squared equals 1 is one of them. Something roughly like that. That's pretty bad. Semicircle, that's okay. And then x squared plus y squared equals 4, so this one has a radius of 2. Okay, and I should probably label them. So we'll call this guy x squared plus y squared equals 1, and we'll call this guy x squared plus y squared equals 4. And this is our semi-annular region, so it goes in the positive orientation because of our little circle that we see, so that means it goes from here to here to here to here, and this forms our region D. So let's describe that using polar coordinates, probably the easiest thing. So it'll be all of the r thetas such that it looks like r goes between 1 and 2, because we're in between these guys where the radius starts at 1 and ends at 2. And it looks like theta goes only up until 180 degrees, so it goes from 0 to pi. So that means my line integral over c of y squared dx plus 3xy dy is equal to my double integral over d of the partial with respect to x of 3xy minus the partial with respect to y of y squared, and that's all by Green's theorem. So this would be the double integral over d of y dA, so that works out really nicely. We just have 3y minus 2y. Beautiful. So that means in polar coordinates, that'll be the integral from 0 to pi for theta, 1 to 2 for r of y is r sine theta, and then dA is r dr d theta. And that'll be the integral from 0 to pi of sine of theta. Just fix that. And that's just times the integral from 1 to 2 of r squared dr. It's got an r there and an r there. And that'll be minus cosine theta from 0 to pi 1/3 r cubed from 1 to 2, and that's just 14/3. The cool thing about Green's theorem is that it's even more powerful than it seems. Turns out we can actually extend it even if we do have a hole in our region. So what we do is we chop up the region. We cut it up into 2 pieces where when we have our region D, each of those pieces has no hole in it. And then we apply Green's theorem to both, basically. So what happens is we do Green's theorem on the, let's say, the top one. So that would be this guy over here. We do Green's theorem on the bottom one. That'll be this guy over here. And then notice what happens. When we convert to the line integral over this part cancels in the other direction. Because remember, you're traversing along this way for the top one. And then for the bottom one, you traverse in the opposite direction. So both are still in the positive orientation because of the way that this goes around positive. However, the cut parts end up canceling because those become opposite. So when we convert using Green's theorem, notice the line integral over d prime and the line integral over d double prime just become the line integrals over this piece this piece, and this piece. That's all you have left. So that means that we're doing the line integral over the outer curve and the line integral over the inner curve. And that's all there is to it. With line integral over C1, line integral C2, and altogether it's just line integral of the entire curve that we're given. You just have to be a little bit careful here. Notice that the curve C1 is in this nice positive orientation over here, but the curve C2 is actually in the reverse orientation compared to C1, I mean, because if you're a person standing, you still want the curve to be on your left. So notice that it still makes it, I mean, not the curve, the region D. You want all of the region D to still be on your left side when you're pointing to it. So notice in order for that to still happen, because you're now on the inside of the region, you're walking around the hole, you must have to point over here, so this arrow must have to go in the opposite direction as the arrow on the outside in order to preserve everything. So you just have to be a little bit careful. If this arrow is pointing the other way, then you have to reverse it first before you can use Green's theorem, so you've got to throw in a minus sign. Okay, say that we have f of xy equals minus yi plus xj over x squared plus y squared. Let's show that the line integral is actually 2 pi for every positively oriented simple closed path that encloses the origin. So an arbitrary path would look something like this. Let's see. Okay, so that encloses the origin. That could be our curve C. So then this is our region D. But how about we modify it a little bit, because taking the line integral or even taking the double integral over this arbitrary region would be quite a bit of work to actually show that equals 2 pi. Taking the line integral over a circle is probably much easier, so let's just draw a circle inside. We'll call that curve C prime, how about? And we'll make this positively oriented C, and we'll make C prime positively oriented too. So then we're going to try to show that the line integral will be the same over the arbitrary region as it would be over the circle, because if this is true for every simple closed path that encloses the origin, then it must be true for the circle as well as for this weird path. So if we can show that this weird path has the same integral as this, and then we can show this one has an integral of 2 pi, then we're good to go. So how about we write out the line integral over C of p dx plus q dy plus the line integral over minus C prime of p dx plus q dy. Notice I'm doing a minus because the way that I wrote it, C prime has a positive orientation for the inner part over here. But what I want to do is I want to apply Green's theorem to this region D where the circle cut out. So I need this to point inside. So I need to reverse it so that these lines, when I cut it up, cancel as we previously saw. So I throw in a minus. So this will be the double integral over D of the partial of q with respect to x minus the partial of p with respect to y dA by Green's theorem, which is the double integral over D of y squared minus x squared over x squared plus y squared squared minus y squared minus x squared over x squared plus y squared squared dA. Okay, so that's fantastic. This is the same. So it's 0. Great. So that means that the line integral over C of p dx plus q dy must be equal to minus of this guy. But if I throw in a minus, that's the same as just making another minus over here and making this plus. So it must be equal to the line integral over C prime in the positive orientation of p dx plus q dy. Because if this thing equals 0, just subtract this to move it to the other side and then throw in another minus. So that means that my line integral over c must be equal to my line integral over c prime. So if I can show the line integral over c prime is 2 pi, then I'm done because I've shown that line integral over c is 2 pi. So let's just compute the line integral over a circle. That shouldn't be too bad. How about we parametrize our circle? Remember that we have our curve equal to whatever the radius is, let's say a, cosine t for the x component, plus a sine t for the y component, where t goes from 0 to 2 pi. So now we have the line integral equal to the line integral over c prime, and we'll calculate that as the integral from 0 to 2 pi of the dot product f of r of t dotted with r prime of t, which is just going to be the integral from 0 to 2 pi of minus a sine t minus a sine t plus a cosine t over a squared cosine squared a plus a squared sine squared t. Notice all I've done here is return to the f they gave us. So minus y is minus a sine t, plus x is plus a cosine t, x squared plus y squared is how we get our denominator over here, a squared cosine squared plus a squared sine squared, and we dot it with a cosine t and a sine t. So this is absolutely wonderful because we get a squared over here, sine squared. We get a squared cosine squared over here. We factor out a squared on top and bottom. So we have a squared times cosine squared plus sine squared, so that's just a squared times 1. But then we have a squared on top and bottom, so even the a squareds cancel. And we end up with the integral from 0 to 2 pi dt, which is 2 pi. So that means this integral is 2 pi, exactly as we wanted.